Hey, good morning, everyone. Thanks for being here. We're going to get off and into 2.5, thermal energy. 2.5. Join me. Pull it up on Amplify. Let's get started. So I've got 2.5 pulled up. I've been looking at it and looks pretty good. Let's go ahead and start from here. If I click on, and once I log into Amplify, this is where I end up. My choices take me to thermal energy. What I do notice is that when you bring up Amplify, it brings it up where you left off. Am I right? If that's the case, we're down to 2.5. So if it brings you up into less than 2.4, this little arrow takes you over to 2.5. Thanks, Aiden, for letting me know about that. And let's get started. I have looked into here and we will be doing a demonstration with a paper modeling tool. If I bring this up and let you see, I'll be working with this in a moment when we get to our hands-on activity. I'll guide you through it. I don't think you'll have the paper, but you'll see how to work this paper, because I don't think this is the last time you'll see this type of model. So it'll be good to know how to use it when we get there. So let's begin with the warm-up. Students practice using the term equilibrium by determining whether three systems are at equilibrium or not at equilibrium. Okay, quick 5 minutes thinking about equilibrium. Below are visual representations of three pairs of samples, A and B, C and D, E and F. The samples in each pair are in contact. Based on your interpretation of the diagrams and your knowledge of kinetic energy transfers, label each pair of samples as, quote, at equilibrium or, quote, not at equilibrium. So remember that the definition of equilibrium is a balanced state at which a system is stable, such as when two or more samples are at the same temperature. Refer to the key concepts posted at the bottom of the screen. Oh, I misread this. Refer to the key concepts posted to the classroom wall if you need help. Remember, another place of finding this is in our playlist. The key concepts are always right here. Okay, so when we got to this idea of stable, in which all of the molecules are moving at about the same speed. Okay, so the average movement is temperature, which means the temperature would be the same, which means the total energy would be the same. Or no, the average energy, the kinetic energy would be the same. So not the total kinetic energy. We're not there yet. But back to here. When you finish labeling the images, complete the sentences at the bottom of the screen. There we go. I mixed this sentence, the top of this sentence, refer to the key concepts at the bottom of the screen. You see, don't do that. Well, what do you think about sample A and B? They look to be the same color. In fact, they look to be just a copy of each other, meaning that everything in sample A is pretty much the same as everything in sample B. Well, the same means at equilibrium, stable. These two ideas, a measurement of the average kinetic energy of each of the molecules, okay? These two numbers are the same. So whether you're measuring in Fahrenheit, Celsius, or Kelvin with a K, this degrees Celsius here is equal on both sides. These two samples have the same. And when they're the same, we could say that this system is at equilibrium. And then finally, what the heck? Look at this. Are these, they're definitely not the same, but look in each one of the samples. Each of the samples have differences. So what do we do now? Well, remember that temperature is a measure of the average. So what's the average inside sample E? Well, this sample E looks to be all ones, twos, and threes. Look at sample F. We have, instead of one, twos, and threes, we have ones, threes, and fives. There's a lot of fives in here that there aren't in here. So which one, I see both have 9 molecules? Well, here's where we do a little bit of math. If we say 3 plus 1 plus 2, we come up with 6. 3 plus 1 is 4, plus 2 is 6. Well, here's 3 plus 1 plus 2, so that's 6. And here's 3 plus 1 plus 2, so that's 6. Well, there's 6 and 6 and 6. That's 3 times 6. Well, 3 times 6 is 18. So 18 divided by 9 tells us that the average energy in each one of these molecules, if these were those little energy blocks, each one of these could all have exactly 2, 4, 6, 8, 10, 12, 14, 16, 18. So we could spread these little energy blocks out equally, and all of these molecules would have 18. Well, that's not what we find over here. We find over here that each row is different. So how many ones do we have? How many fives do we have? And how many threes do we have? We have 3 of each, don't we? So let's count up all the fives. 5, 10, 15. Now let's count up all the threes and add it to 15. 15 plus 1 3 is 18. Plus 3 more, 19, 20, 21. Plus 3 more, 22, 23, 24. So we've added up all the threes and all the fives, and we've come up with 24. Now, 25, 26, 27. All right, so all of these numbers add up to 27. How many numbers did we add together? 1, 2, 3, 4, 5, 6, 7, 8, 9. What's 27 divided by 9? 27 divided by 9 is 3. So the average temperature of this sample is a 3. Well, what's greater, 3 or 2? Well, you know that the sample F has more energy than sample E. Well, that tells us it is not equal, is it? So these two samples are not at equilibrium. Will something happen to this one? Yes, over time, this will change as long as they're in contact. These higher average molecules will share the extra energy they have with these molecules on this sample because they're in contact. And eventually the kinetic energy here will, oh, look at that, it got big, will spread over to here and share some of those. We saw an example of that yesterday. Hit the hand in button. Oh, wait, there were questions, my bad. The average kinetic energy of the molecules that make up sample E is 2. The average kinetic energy of the molecules that make up sample F is 3. There we go. Now we can update that. Now, a word relationships. This is where we split up into partners. Hi, partner, you're one of my partners. I'm going to take a turn with you. At first, you'll listen to me, and then I'll talk. And then we'll switch that around, and you'll listen to me, and I'll talk. Okay, so we're going to use some of the words from the word relationship cards, which are right below here in this word bank. We'll we may use the same word more than once, but we want to use all of these words. There are many different sentences that could help to answer the investigated question. But what is that question, the investigated question? Here it is. Why does the transfer of energy between two things stop? So that's the thing we want to answer. Why does the transfer of energy between two things stop? You know, when we watch all the examples in the sim, when two objects come together, eventually that transfer of energy stops. Why is it stopping? Well, let's see what we can do right here. I see the word equilibrium. I see the word average, kinetic energy. I don't see the word temperature. So let's begin with the average kinetic energy of an object is the average speed of the molecules of an object. When we measure the temperature and it has greater temperature than another object, we would say that the average kinetic energy of the warmer object has a higher temperature. The average kinetic energy of the cooler object would have a lower temperature. Now, this kinetic energy comes from the actual collisions of the molecules that make up that object whose temperature we're measuring. This collection of molecules creates a system of exchange of energy, whereby when we take one or more objects and place them in contact with each other, the molecules of one object will share the kinetic energy that it has to molecules with less energy. Remember that the transfer of this energy always takes place from higher states of energy or warmer molecules and transfers it to cooler molecules or molecules that have a lower kinetic energy. We always move from high energy to low energy. And this takes place until all of the molecules have the same kinetic energy. That kinetic energy, because it's the same now, means that there is no higher energy in a molecule to share with another molecule of lower kinetic energy, because all of the molecules have the same energy. We call that stability. When there's stability, there's nothing to share between molecules. Since all the molecules have the same amount of energy and that's where they want to be, there's nothing that wants to move from one molecule to the other. All of the molecules and all of the energy in the molecules are all stable, and so nothing will change. We call this equilibrium. Thanks for hanging out with me. Let's move to activity 3. Now, activity 3 starts with a letter from a concerned parent. Dear Mr. Chang, I'm worried about your proposal to install a groundwater heating system at my daughter's school. Here's another person who's concerned. I don't think that water at a temperature of 30 degrees Celsius has enough energy to heat the school. If the school is too cold, the students won't be able to focus on learning. I think we've seen this letter before. Well, people have concern about that. If we're getting water from under the ground and it's 30 degrees Celsius, is there going to be enough energy to heat the school? You see, that's the thing that we need to prove. Otherwise, we will have a lot of very concerned parents and concerned students too. So we need to work on this question. Students model how water from the groundwater system would warm the air inside the school. Now, all you have to do, since there is a next button here, is watch. There is no modeling tool for you, and there's nothing for you to do but watch. So we're going to create a model that shows how the water in the groundwater system will warm the air inside the school. So we need our model. Here's the model I'll be using, and in a moment, we'll get started with that. I'll meet you at the demonstration table. Okay, so I'm back at the demonstration table, and you can see that object one having little energy bits of energy. Remember, these are not the molecules. The molecules are the circles, okay? So this molecule has a little bit of energy. This molecule has a little bit, 2 little units of energy in these molecules. Each one is at equilibrium with its neighbor. Now, this object is made up of 4 molecules, and here's another object, object number 2. This object is made up of the same amount of molecules, but as you can see, this object has a lot of units of energy in each. In fact, if we do this and group these in smaller numbers, you'll see each molecule has 6. Now, these molecules are all equal in terms of the amount of kinetic energy they have. What that means is that this object, all the molecules in this object are all at the same temperature. Now, compare object 2 with object 1, and you notice object 1 is at a cooler temperature. There's less kinetic energy in each molecule. However, object 1 is in equilibrium with itself. Because all of these molecules are in contact with each other, if this were to happen, it would quickly, through higher vibration on this side, share that energy with that one. Remember, energy gets shared from higher to lower when they come into contact with other molecules. So if we put these 2 objects together, now these molecules vibrate against these molecules and share. Now you can see now these molecules have more than this. So it wants to share until it's equal. Now another one gets shared here. Now this one has 3, which allows that to have 3. But look over here. There's 4 and 4, which means there needs to be something here that needs to get shared, because there's more energy in these molecules, which use the kinetic energy to share with these. Now that these all have 5, they're back at equilibrium. But look, this is in contact with this, and 5 is more than 3, so these get shared. Now, these are 4 and 4, and they're happy, but 4 is greater than 3. So what happens? Well, this 5 gets shared with this. Oh, but it can't, because 5, oh yeah, 5 makes 4, but now see, this is somewhere in between. So what happens? Well, this has to share, oh my goodness, with this, which shares with this. And now there's 4 and 4 and 3 and 5. And now through all of the vibration, eventually it all spreads out nice and evenly. It kind of works in a much quicker way than that. But that's the model of equilibrium. Well, to answer this question, how do we heat the school with 30 degrees Celsius water? Well, in the morning, you see, we have a modeling tool. In the morning, in the afternoon. So we know that the air inside the school in the morning, as far as this goes, shows that the molecule speed And I think we need to get a little closer here. Um, so let's do that. Bring this down and maybe switch our camera. To this camera. Now let's see if we can continue working. Yes, I think so. So we have a morning situation. We have an afternoon situation. We have thermometers. We have, what is this? Energy transfer. Okay, so in the morning, the warm water below the school is at a pretty warm temperature. You see that it's moving quickly. So this is a 5. If we put this here and call it a 5, what would it be here? Well, it would be a 1. Now, based on what we know, when we come into school in the morning, the water starts circulating through the pipes that come into contact with the air inside the school. Well, what happens? These molecules, because they're at a higher energy, starts to transfer energy to the air in the school. Once this starts to take place, the air in the school gets warmer. Now, based on what you know about a system, when two objects come together to make a system, the higher kinetic energy molecules have collisions. The water in the pipes collide with the pipe itself and vibrate and warm up the pipe. The warm pipe comes into contact with the molecules of air, and that warm pipe starts to rise the temperature of the molecules in the air. Well, what happens at the end of the day? Well, we have the same number of molecules. We didn't let water leave the school building all day long. It just got pumped through the building again and again and again. And then at the end of the day, everything should reach equilibrium, meaning that no energy will get transferred between the water and the pipes. But what will happen? Well, the water will get cooler and the air will get warmer. But since no energy is created or destroyed, this is 5 energy units times 6 molecules. 5 times 6 is 30. So you see you have 30 units of energy here, and here you have 1 unit of energy times 6 molecules. That equals 6. Well, what is 30 plus 6? 30 plus 6 is the total amount of energy in this system, which means that the same number has to be over here. Well, I need to spread 36 of these little units out amongst 12 molecules. Well, 12 goes into 36 3 times, so let's count it out. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, and 36. This makes each one of these a 3. And so the temperature here would be a 3. A temperature here would be a 3. And at the end of the day, all of the energy that is available here was spread to here until everything got to be the same. And then the system stops working. The water gets pumped back into the ground and new water is pumped in for the next day to start all over again. So that's the way this model works. I'll stop and meet you at activity 4. So back to sharing my screen. And we'll go to number 4. I believe there wasn't a hand in. Nope. Ah, there is a next activity for part 3. So back off the demonstration and back to the questions here. Answer the questions below using your model and the new key concept. Here's the new key concept. The molecules of a system will transfer energy until the system reaches a stable state known as equilibrium, in which all of the molecules are moving at about the same speed. So if we write a response to David Lee's letter, we would want to explain how the groundwater system could heat the air in the school. So, dear Mr. Lee, water at 30 degrees Celsius can heat the air in the school to a comfortable water at 30 degrees can heat the air in the school to a comfortable temperature. The reason why is that the tank of water has enough I'm going to change this, that the tank of water is large enough to hold the total amount of heat necessary to increase the air temperature in the school Remember that the molecules of the water is what is holding the heat. Now, in our demonstration, the heat inside the molecules were the little cubes, the plastic cubes. And so if there are enough of those to spread around, and that temperature at the end, the average amount of kinetic energy in each molecule, if each molecule of air comes to equilibrium with the water, the temperature would be in between the air temperature at the beginning of the day and the water temperature at the beginning of the day. Remember that in the paper model we just looked at, the air temperature was 1 and the water temperature was a 5. We'll go on to say if the system is balanced, the temperature of the water and air will be the same at the end of the day when the system has reached equilibrium. That means all of the molecules are the same temperature. And that's what we did with our paper model. All of the molecules at the end of the day were all of 3. This means that the water will have lost its energy and the air will have gained the energy lost from the water. The water's giving up that energy. The temperature will be the same, and this equilibrium temperature, which means the temperature that's at the end of the day when the system is at equilibrium, the temperature will be the same. This temperature will be somewhere between the 11 degrees centigrade of the air and the 30 degrees centigrade of the water that the system starts with at the beginning of the day. Okay? So that would be our response. Sincerely. Mr. Power. Oh, I have something here that's not making sense. Between 11 degrees of the air of the water. I wonder why it thinks that's misspelled. Look up the word of. Expressing the relationship between a part and a whole. The air temperature of the air. Between the 11 degrees centigrade of the air and the 30 degrees centigrade of the water. I like it. I'm going to leave it that way. Okay. Now, the real question is, what is that equilibrium temperature? Explain what would happen to the air temperature at Riverdale School if the groundwater system would use the term stability and change in your explanation. Well, I think this is kind of it, isn't it? How the groundwater system could heat the air in the school. Explain what would happen to the air temperature if the groundwater system would use stability and change. So let's go and use stability and change in our paragraph, and then we'll use the same answer in both. Okay, can't beat that. So if the system is balanced, the air temperature will be the same at the end of the day when the system has reached equilibrium. This is why the tank of water is large enough to hold the total amount of heat necessary to increase the air temperature in the school as the system attempts to become stable. Okay. If the system is balanced, the temperature of the water and air will be the same at the end of the day when the system has reached equilibrium. This means that the water will have lost its energy and the air will have gained the energy lost from the water. This equilibrium temperature will be somewhere between 11 degrees Celsius and of the air, between the 11 degrees Celsius of the air and the 30 degrees of the water that the system starts at the beginning of the day. These temperatures change until they meet each other at this stable temperature. So they change until it becomes stable. So let's take this and copy it down here because it answers all of these questions. We'll hit the hand in button and move along. Next activity. 2 heating systems. Here are the 2 proposed heating systems that the principal is considering. Based on what you learned so far, discuss with a partner, hey partner, which of the 2 systems you think will do a better job of warming Riverdale School and why you think so. Then answer the questions below. Okay, so I'll be your partner, and I think at at this point we think we have to choose one or the other. Okay, so which one would you choose? Well, you might think this. Hey, check this out. Look, the thing here is the same. The starting air temperature is 11, okay? And what we just wrote about was a system that had a 30 degrees Celsius water. Well, check this one out. Look at this. This is 39 degrees Celsius, okay? But here's something that we also know, and they're not really showing us, is the size of this tank. Now, this is warmer water, so it should raise that equilibrium temperature because it's got more energy to share with the 11 degrees Celsius air. So as this cools down, this should warm up. But how far will this cool down and where in the middle will this meet? You see, I think it has to do with the size of these tanks. This tank is quite a bit bigger. In fact, it won't fit inside the building, so they have to put it underground. Now, it's a bigger tank, but it's cooler water, just a little bit cooler. But is it warm enough? See, they both do the same thing, pump warm water through these pipes. At the end of the day, though, this gets recirculated back into this tank. You have to heat it up using some kind of fuel, right? Because there's nothing here to heat it back up. At the end of the day, it's going to be cold water, or water that's the same temperature as the air in the school. So at the time when no one's in the building, the boiler will heat this up, and at the beginning of the day, it will push through here to heat the air in the schools through the warm pipes. Over here, we see that there is no heater. This is just the temperature that they're pumping out from the ground. I think this well right here, this pipe goes down deep enough to find water warm enough to fill up this tank with water that's almost as warm, but not quite as warm. So now it pumps a little bit cooler water through here, and then as it does, it just pumps it back into the ground. Now, it's not wasting that water because that water eventually gets filtered through all of the sediment, all of the soils between the surface and where the reservoir is of groundwater that this is pumping from. Okay, so this is like a big cycle, a much bigger cycle that the groundwater goes through than this water here. So what do you think? Think about the paper model that we used. And did we multiply temperature by the number of molecules? Well, when we multiply by the number of molecules, you can see a bigger tank is going to give you a bigger number. Suppose these were the same temperature. See, 30 and 30, if that was the same, a bigger tank would give more energy to the air in the school. So think about that as you make a decision. Go ahead and pick one. I'm not going to tell you one. Well, maybe I will. I think that the size does matter. So if this is big enough, even though it's cooler, it could work, but it has to be engineered. Okay. So I'm going to say not the water heater system, but for now, I'm going to bet on the groundwater system because it seems the most surprising. If I pick it, if it's true, I would be amazed. So hand that in, and we're up to our last activity. We're going to revisit and revise a statement from the anticipation guide. Below is a statement from the anticipation guide that you completed at the beginning of this unit. Okay. So that's where we got this. I think it was in lesson 1.2. Look back at the statement and decide whether you agree or disagree with it at this point. Then try revising the statement to make it more complete or correct. Okay. So we want to see, do we agree or disagree? And we want to revise the statement to make it more complete or correct. Okay, so when something heats up, new energy is created. No, I disagree. Now I see what the instructions say. Now we need to make this statement correct. So let's copy it and paste and changed. When something heats up, energy is added to that thing from another warmer object that is in contact with the first thing. This is like thing one and thing two. When something, let's do this. When thing one heats up, energy is added to thing one. This is like Dr. Seuss, right? Thing one and thing two. So we're gonna, when thing one heats up, energy is added to thing one from another warmer object, thing two, that is in contact with thing one. And when something cools down, like thing two, energy is given away to a cooler object, like thing one. So let's see if this makes sense. It sounds a little confusing, doesn't it? When thing one heats up, energy is added to thing one from another warmer object, thing two, that's in contact with thing one. Okay. And when something cools down, like thing two, energy is given away to a cooler object like thing one. So when we put thing one and two together, if thing two is hotter, it's going to give that energy up to thing one until they both reach the same temperature. So we disagree. Here's our new statement. This is what we're going to put here. How could you revise the statement to be more complete or accurate? That's how I would do it. Thank you, folks. I hope you've watched it this far, and I hope you're following along, because it's getting kind of interesting. Take care, everyone. Let me stop my share. I will meet you in the next lesson. Take care, stay well, be safe, and hug someone you love that's in your bubble. Take care.